Once again for inviting me here. So I'm going to talk about some work I have been doing with Ashok, and sort of broadly I will call it classical limit of soft theorems. So I will explain all the words that are there in the title, but let me first try to tell you the kind of the question we are trying to ask is the following: that suppose you consider a classical scattering process. For example, say some 2-2 scattering. So you have some two large objects like black holes or neutron stars, and they come collide, and then they scatter, and then they produce some radiation. So sort of the most natural question we would like to ask for this kind of processes is that, given if you give me some bin, so if you give me, say, consider some, so you have some detector at some point in the sky, which let me locate, so consider some detector which is located by some vector n hat, and consider some frequency range omega 1 plus delta, between omega and omega plus d omega basically. Then the kind of question we want to ask is, what is the energy emitted in this sort of in this range? So what is the energy which is emitted around n hat in some solid angle delta omega, and the frequency range omega 1 plus delta. So it's kind of a very sort of basic question we would like to ask for these processes. Of course, in general, this you cannot compute analytically because depends on the details of the scattering. But what I would like to sort of argue in this talk is that if omega, so this is kind of the key result of the talk that I will spend a lot of time explaining. So the key point is that if omega is much less than, let me just say, characteristic frequency of the system, for example, depending on inverse of the impact parameter, then this energy that you want to compute can be computed actually just because of the consequence of some theorems in quantum gravity, which are called soft theorems. So then these results are, okay, let me just write it. I will explain this word later, universal, by which I just right now mean that they don't depend on the details of the scattering process, but only on the sort of initial and final moment and angular momentum. So the fact that this happens is because of what we call classical limit of soft theorem. Which is what I will try to explain for most of my talk. So to begin with, what I will do is I will try to do this for d greater than 4. And then once we understand d greater than 4 case, then I will go to d equal to 4 case, which is sort of more interesting and more also confusing. Because the IR divergence is here. And here what happens is that, so for the d greater than 4 part, we will use the soft theorems to get understanding of the classical radiation. But in d equal to 4, we don't really have a detailed understanding of soft theorems except today Ashok and Biswajit had a paper. So we will use the classical radiation theory to kind of get an understanding of the soft theorem. So in d equal to 4, we will reverse the logic of it.
What was beta?
So okay, this is just a parameterization. So between, usually we write omega and omega plus d omega, but just for convenience of formula, I'm writing d omega as like omega times a small parameter delta. Okay, so let me try to now, so this is the goal. Right now, the first goal is to understand what do we mean by classical limit of soft theorems in d greater than 4 dimension. So let me just briefly recall, I think most of you would know, let me first briefly recall what are the soft graviton theorems. So suppose I give you some scattering amplitude with some n particles, and let me just restrict for simplicity to 4 particles, like 4 scalar particles, for example, and 1 graviton, so 4 plus, so m5. So the particles have momenta p1 to p4, and there is a graviton which has polarization epsilon and momentum k. Then in the limit that the momentum becomes soft, this amplitude factorizes, and it can be written in the following form. where this, so up to order omega in the, okay, sorry, let me explain. So where S0 epsilon k, which is called Weinberg soft factor, is just given by the sum over all the particles so as you can see, it goes as 1 by omega. So it really is a Laurent expansion in the frequency of the graviton, and epsilon S1. So this is just a function of the kinematic variables, and S1 is in contrast to S0. It's like basically a differential operator, and is given by where this J is nothing but angular momentum of each particle, which includes spin as well as orbital angle. And the nice thing about soft theorems is that in d greater than 4 dimensions, these are exact theorems. So this is an exact statement in perturbative quantum gravity that any amplitude will factorize to this order. S2, there is a factorization up to order S2, but S2 is not quite universal. So let me just write down what I mean, although we won't really use S2 in this talk. So S2 really is sum of two parts. One which has a nice form, is given by, so it's square of angular momentum operator, and as you can see, it's order omega because there is 2 k's in the denominator and 1. But plus, it can have other terms which depends on the sort of the one loop effects in the scattering amplitude, and if you have some irrelevant interaction like higher derivative interactions and all. So it's what we could call it like quasi-universal. So there is a factorization, but the factor is not as nice as the one that up to subleading order. So if you restrict up to this order, these are called subleading soft graviton theorems. So this is for a single graviton, if you have one graviton emitted. But the interesting thing about this is that we haven't really said anything about these particles, like what they are. They could be composite objects, black holes or anything, because it only refers to the momentum of these particles. But in the case that these objects are large, then obviously we naively expect that the number of gravitons will emitted will also be large. It will not be one graviton that's emitted. So what we really need to understand, if you have some large object scattering producing soft gravitons, is some n graviton theorem, and that also is well understood now. So let me just write that down. So now we want to sort of generalize it to n soft graviton theorem. Yeah, after that there will be no factorization. Yeah. For any theory of gravity. Well, S2, the form is not universal for that is, but it's not even like, it's not, I can say a bit more about S2. S2, it's not like even completely sensitive to, it's not different for every theory. There are a finite number of higher derivative interactions for which it will change.
What's the difference from that point of view from S2 and S3?
Well, there will be no S3, there will be no factorization in the sense that there could be, I mean, you could write, if you go to this order, you could write the amplitude as something which looks like cube of angular momentum, S4, plus a remainder term, which won't look like a factorization at all.
And just can you remind us where that came from? I remember either you or Ashok gave us a talk on this covariantization.
Yeah, Ashok gave the talk, yeah.
Okay. From that point of view, what is the difference between 2 and 3?
Well, you see, the point is that if you, okay, so if you want to go to this order, you are going up to order k square, which means that you have to go to up to order Riemann. So you really have to look at, if you have a process from which a soft graviton is emitted from one of the internal lines, then you have to know the details of the Riemann coupling because k square is there, and that's completely theory dependent. This doesn't quite tell you, doesn't factorize, but if you look at individual theories, then you will see that there is a remainder term which doesn't even factorize actually.
So it's like the minimal coupling versus non-minimal coupling. Is it kind of from k square onwards, you can have other things which are not obtained by this covariance.
Exactly, not just obtained by you really have to, for each theory per theory, you can compute this, but there is no real form for this because of what you just said. But I think there is more to the story in the sense that
it was exactly Gautam's intuition that led me to think that and every order there will be a finite number of vertices. If it was just covariantization plus various powers of curvature,
Yeah.
at any given order there will be a finite amount of ambiguity.
Okay, but that's not the case.
But you're saying it's more than that.
Yeah, it's more than that. Yeah. Okay, so let me now, our interest is not in a single Soft Graviton theorem, but in n Soft Graviton theorem. And again, this is a theorem which was proved in detail by Mrityunjay et al. Ashok. So let me just write the theorem first. So the theorem says that suppose again you look at say some 5-point amplitude. Sorry. 4 plus n point amplitude, P1 to P4, and some epsilon K1 to epsilon and Kn. So n Soft gravitons are emitted. Then again this has a nice factorized behavior. This theorem is understood only up to subleading order really. There's not much known at subleading order, so I'll just avoid this part. And so this, it turns out that this can be written as, it looks very nasty. Just write it down. So there is a term which is product over all I 1 to n S0 epsilon I Ki. Plus this is really the leading term because all the terms are leading soft factors. Then you get a term which is j equal to 1 to n S0 epsilon j kj and 1 S1 because one order subleading. But if it was only this, then it would be nice. But there is more nasty stuff sitting here, which let me just first call it contact terms. I will write them down now. Sorry, that's a very good question. Sorry. So this is in the, if you are taking them to be soft simultaneously. Yes. Yeah, you can take them one by one. Then actually, if you take one by one, then these terms drop out. I mean, not all of them survive. Yeah, some of them survive, some of them don't survive. But let me just say that this is actually I can say maybe this is not the best answer. Actually, this is the most general. I mean, given this, you can take any order. You can take simultaneous, but you can also take one by one. And this contact term, then they are as follows. Again, some over J and K, J and L. When some, okay, all the details are not very important. I will just write it down. I not equal to JL S0 epsilon I Ki 1 over K dot Pj plus PL, blah, blah, and then some terms which, let me just write it as some function f which depends on Pi, Pj, and sorry, I wrote something wrong. This is PA dot Kj plus Kl, and then P A Kj Kl, and then sum over A. I mean sum over all the particles.
This result was also obtained by covariantizing?
Yeah, this was obtained in two ways by them. One was covariantizing, and one was what is known as CHY formulation for scattering amplitudes. Yeah.
So this contact terms meaning that you
Yeah.
have the rest of the diagram in two.
Yeah, I was
elements
about to
that
say.
are not,
Yeah, so this contact term arises when you have sort of two gravitons coming out of a vertex, or if you have one soft graviton which in its turn emits another soft graviton. So all of them give rise to this. All of them sort of combine to give you this contact term. So diagrams, exactly as I was saying, diagrams like this, and also diagrams like if you had one soft graviton itself emits another soft graviton.
Is the contact term non-zero only when Ki is Kj?
No, it's non-zero in general. Yes.
So it's not contacting momentum.
It's not contacting momentum space. Yeah. Okay. Sorry. Thank you. Yeah. So it's a general. It's yeah. it's for any arbitrary choice of, generically it will not be 0. But the nice thing is that it's still a universal theorem and it factorizes and theory independent.
And has this formula also been obtained by Tahar's methods? I think it's discussed. Not for multiple stacking.
Yeah. No, this is this is exact statement for the quantum gravity. So I think, I mean, this is really true in string theory in that sense.
The CHY check was true level.
It's at tree level. CHY is tree level, but covalentization procedure that Ashok did is for any theory which is UV complete. So basically for string theory. Because it's insensitive to the nature of these external particles. They could be anything.
There wasn't more than 4 higher factors.
Oh yeah, no, I was just, because I am going to be, sorry, I should have said that. I mean, because I am going to focus on this in classical theory, this could be any.
The covalentization idea is very interesting.
Yeah, very general, yeah. So this looks like a kind of a complicated formula to play around with, but as we will see that in classical limit it really simplifies remarkably. So let me try to now explain what we expect in when we take the classical limit. So what we are saying is that our objects P1 to P4 are classical objects. So their masses are large in Planck units, and then we expect the following kind of natural expectation we would have is the following. One is that the number of soft gravitons emitted sort of goes to infinity in classical limit. That is a kind of a natural expectation, because the more massive the objects are, more graviton they will emit. So if the mass is infinity in Planck units, then you will expect the number to also scale with the mass. And the second expectation is that, I mean, no, this is not, okay, let me just say it. The energy radiated in soft radiation, in radiation should be smaller, so much small compared to masses of the objects. This is not an expectation for a generic classical scattering, but we can only hope to apply soft theorem if this condition is satisfied. And I'll tell you why. Because of the fact that if the energy radiated was comparable to the mass of the particle, then that energy itself can emit some gravitons. And then we have to include that energy into this P1 to P. But we don't have any information about that. So we can't really apply, if the radiation energy was comparable to the masses, then we cannot hope to apply the soft theorem. The soft theorem could only be consistently applied if.
But the soft theorem is general, right? So the P1 to P4 can also be.
But yeah, but we would need the knowledge. I mean, in general, you can apply. I'm not saying soft theorem will break down, but it won't be of much use to us, because we won't have a. Then we have to know exactly in which direction how much energy is radiated, etc.
And it will scale much faster than omega over t. So omega over m. In that you would have multiple many gravitons with soft gravity.
I will give you the scaling for. Are you asking for how n scale with mass?
No, I'm saying that I thought you just said that.
Yeah, sorry. So this is a natural. Okay, let me distinguish between this one. So this is an expectation, and this is a requirement. This is a requirement because if this is not true, then if you have some energy radiated which is appreciable as the mass of the particles, for example, then that energy in turn could emit some soft gravitons. So in this external configuration that I have to include that radiated energy also as part of the object which is emitting soft gravitons. Now as Prahar is saying, of course I can do that, but since I don't have a knowledge of detailed flux of that, this formula will not be of that use to us to compute anything. So yeah, if you know that in this much energy is radiated appreciable in this direction, then we can, one of the P's can be that flux, for example.
You knew that, you'll also know the soft.
Yeah, okay, sorry, yeah, that's true. Then it will be a circular. Okay, so and now what? But intuitively, suppose this was true, that energy radiated is much smaller than the mass of the particle, then okay, at a 0th order you can sort of vaguely see that contact term which will be smaller compared to the other term, because contact terms are coming when soft graviton is emitted from the other graviton. But if the energy radiated is small, then we can neglect the contact term. So let me at the 0th order, let me just neglect contact term and play around and see what I get. So what we want to do is we want to sort of come up with a self-consistent scheme when we take this classical limit, assuming this is true. Yeah, that's why it's a very 0th order intuition. You're right. So that part, this argument I cannot explain, but we will see that if this is true, then indeed contact terms are small. But let me start first by assuming contact terms are not there, and then I will tell you why it's all consistent.
And this requirement is not very special or anything, right? What sort of scattering?
Yeah. So we will see in what sort of scattering. Yeah, thank you. So okay. So we will, of course, in a generic scattering process, this requirement obviously will not be satisfied. But we will see that there are two. So I will show this. There are two classes of processes in which this is true, in which this is satisfied. Two is satisfied. One, when impact parameter is much larger than the Schwarzschild radius. This is m to the power 1 by d minus 3 naught. If m is the typical mass of the object. This is one case in which we will say that this is satisfied, and the other case is what we call probe limit, which is in the case of 2-2 scattering, if mass of one particle is much larger than the mass of the other particle, like a point particle in a black hole. So in these two we will see that this.
So even if it gets totally eaten up by the black hole.
Yeah, even then.
Fractional radiation
is small. Yes.
What would be fraction of radiation
in the merger? You mean the I don't know, 5%. I was about to say 10. Okay, I forgot. Okay, so let me try to first, let me assume that the contact terms are not there. Then in the probe limit, we want the radiation will be less than the M2. Yes, exactly, much less than M2. Yes. So assume, let me just assume contact terms are small. Then we can write this theorem. P4 as follows. We can write it as, so okay, we have only two kinds of terms, and up to subleading order, these terms can be written as, so please ask if this is. Because, so okay, let me write I should not have erased this, sorry. So what we had before was product I equal to 1 to n S0 epsilon I k I plus product, sum j equal to 1 to n product I naught equal to j. This is what it was without the contact term. I am saying up to subleading order, if n is finite, I can approximate this by this.
Technical question is
Yeah.
this one contains derivatives in P, and so here it's not acting on S0, right?
Yes.
But is you also assuming that this S1 only acts directly on
Oh, thank you. I will come to this now. Yeah. So let me answer first Praha's question. So S1, as I remember, S1 is a differential operator because it involves the angular momentum. Why is this equal to what I wrote down before? So you can see that, okay, classical, first of all, if you are in classical theory, let me give you sort of two sort of stage answer. One is if you are in classical theory, then J is just x mu p nu minus p nu x mu. So there you expect this to be, I mean, S0 and S1 to commute. But in quantum theory, of course, this is not true. But when you look at S0, S1 commutation, it involves P mu dou by dou P nu. So it brings out 1 power of P, which means it brings out 1 power of mass. It brings down 1 power of mass. So all the correction terms are subleading in the masses, and since the masses are large, they are smaller terms. So I'm saying that you take this, you can rewrite it as what I wrote plus correction terms, but they are all subleading in the masses of the P1, 2, because they always bring down 1 power of momentum.
So in neglecting mass, the terms that are ordered 1 over
M.
as well as terms that, as well as subleading terms?
Sub-subleading we are anyway neglecting.
And for the moment also contact.
For the moment contact term, but contact term we will show, yeah. Okay, so let me say that plus order omega, and maybe I will put 1 by m. Okay, so from now, given the fact that the scattering amplitude is this, we can ask what is the differential cross section, because the reason we are doing this computation is we are sort of heading towards classical limit. We want to find what is the radiation emitted in a given bin, in a given direction. So we can ask what is the differential cross section in a given bin. By bin I mean what I wrote earlier, around some direction n hat with solid angle say delta omega, and in a frequency range omega 1 plus delta. And then this, so we just have to mod square this. So I will write down I will explain, I will write some notation. So we can rewrite this as, okay. Yeah.
So a simplification of ignoring the contact terms is that it becomes particular. Is this right? The contact terms involve the interference between two particles.
Yeah.
And this one is just K by.
Yeah. So this is.
So that looks classical.
It looks classical, yeah. Yeah. And this is what, actually this is the form that you will get if you were just taking, literally just taking consecutive limit, the one that you were saying. And that would have contact terms because of what Prahar said, because S1 and S0 don't commute. So if you write it in the form we wrote, then there would be some contact term coming from. Is that making sense? So this is really what you would get if you just did the what you said, because Shira is now to consecutive limit. So suppose I want to ask, now we want to look at differential cross section. If you are in a given bin, let me put another requirement. Again, this is just for simplicity. And suppose you are looking at like one particular polarization of the gravitational radiation. So all the gravitons are in a one particular polarization. So all these epsilons are, so because the direction is same and the frequency is same, k's are same for all of them. And if I take all the polarization to be same, the epsilon also turn out to be the same. So then this thing just turn out to be equal to S0 epsilon k plus S1 epsilon k to the power n. This quantity is just that. And then the differential cross section, we can just write it as, write it like this, f to the n by n factorial mod f4 square. Where this script f, I mean it involves all our phase space factors and everything. So when this is a formula I will keep here. So f is 1 over, so we are in d dimension, d minus 1, then we will have 1 by 2 omega, then omega to the d minus 2 delta omega, d omega is omega delta, so it's omega delta, and then mod S0 plus S1 square. So is this okay? So this is just coming from mod square of this, and this n factorial is because in classical theory, I mean the gravitons are indistinguishable, so we symmetrize it, and these other things are just phase space factors. Okay. So now, in order to understand what is the classical limit of this, we maximize this. We say that for what distribution of the soft graviton this gets maximized. So we can, from in the large n limit, we can reduce n. I haven't really shown you that the n is large yet, but I will show in a moment. So let just for a moment assume n is large. So I can apply the Stirling approximation.
Is this essentially a coherence state of the soft graviton?
Yes. So assuming n is large, we can show that this probability distribution gets maximized at mod m4 plus n square gets maximized at n equal to script.
E to the power script f a dagger.
E to the power script f a dagger, yeah. Okay. So this is the answer. So the number of soft gravitons emitted in a given bin in the classical limit is just given by this f, and this f is just really this quantity here, which just depends on the single soft factor actually. So although we did all this gymnastics with n soft graviton theorem, in the end the final answer turned out to depend on just a single soft graviton theorem.
The fact that the coherent state is telling you is classical.
That is, yeah, right.
Why did the n is classical? What do you think is one can expect that?
I mean, n should scale. No, what we should expect is that n should scale with the masses of the particle. So we will see that. We will see how n scales. I still have to show that n is. I mean, we would expect in classical theory large number of gravitons to be emitted, right?
Because the energy of a gravitational wave is finite, even though the energy of one graviton is very small.
All of gravitational energy will not be emitted in soft.
So let's say that the energy in soft radiation is finite.
Finite.
The energy of any one soft graviton is very small.
And so, of course, from here we can compute what we initially, the question we asked, which is what is the energy emitted in a given bin, in our bin, and that is given by n times omega, which is f omega. So if you, so now I have made a number of assumptions. I have to justify them, but once they are justified, then this is the answer for that we obtained from soft theorem for the energy emitted in a given bin. So now let us try to understand. There are two things we have to check. One is n is large. Oh, actually three things. N is large. Contact terms can be ignored. And the energy, total energy emitted, not in one bin, but the total energy emitted in all bins, total, is much less than the masses of the.
Sorry, could I ask this?
Yes.
If we did the same thing by getting a nebular,
Yes, yes,
presumably you'll get the same thing without the S loss, right?
exactly, yeah. Yeah.
And there, this should just be a simple statement about Maxwell's equation.
Yes,
Because if you take two charged particles,
Yes,
on
yes.
trajectory,
yes,
and can you just directly prove that statement classically?
yes.
That's an easy.
Yeah, that's it. Actually Jackson does it for the leadings of, yeah, Jackson has the flux formula for S0. Yeah.
Just using the Green's.
Just using Green's function. Yeah.
And that's more difficult in gravity because you need to observe. Because you can't take particles and arbitrary trajectories, which you need to test at every point.
Yeah, that is also true. And I mean, I guess once you, I mean, for a case by case basis, you can do the computation perhaps, which is how we checked it. So we look at a number of cases where we could do the calculation you are saying, and we check that this is justified. But this is telling you that the answer is true.
Okay, case by case meaning, for instance, in the Schwarzschild geometry.
In a Schwarzschild geometry, or two particles far away from each other, just scattering and producing gravitational waves. So in case by case basis, we can check this. But what this is telling you is that whichever Jackson does, he takes a probe particle with large charge q and a small q, and then he looks at the radiation emitted from the small q.
I didn't understand the difference between the direct case and the gradient case.
I mean, what I was thinking, and maybe I'm thinking wrong, is that it's harder to couple classical sources to gravity because you need the
Yeah,
full thing
Yeah.
to be
yeah,
the conservation along with the battery action.
Yeah.
Whereas in electromagnetism, it's easy.
yeah, it's
The
easy.
only
Yeah,
charge is your phone.
yeah,
You just have the well line, not anything in it.
yeah. So because the full, we will see that some cases where we can compute the full stress tensor coupling to gravity, there we will see that even then this. But non-abelian theory, I think Prahar can say a lot more about this. But this ends of gluon theorem itself is much more, because of the non-abelian nature, the gauge group, it's much more complicated than. Oh, I'm sure, yeah. I don't think it's that well.
Yeah, the idea is that the charge corresponds to gravity is itself the energy. So when I'm taking low energy limit, then that charge goes to zero. So even if there are multiple soft limits, all of the extra terms, they end up going to zero. Because like S1, for instance, is proportional to the energy of those ds particle. So
Yes, yes.
Just, I want to get the intuition for where this S0 is coming from. So
Mhm.
what part of the trajectory is contributing?
Only the asymptotics.
So suppose after, since the trajectory is in my hand,
Yeah.
I can have the trajectory be totally straight up.
Yes.
And still it will contribute to the.
Yes. Yes.
So the fact that even though after a point it's floating, the fact that
Yeah.
it had changed.
There's an impulse.
That
Yeah.
will be.
That's yeah. But it yeah exactly.
Okay.
So the point is that the answer for any even a more complicated trajectory is the same as the case that you said in the soft limit.
Right.
Sorry, since the, sorry, get in my head. Now, in the gravity case, you've got a similar term as
Yeah.
the first term, then the S1 term.
Yeah.
And can you roughly say where, in this intuitive way, where the S1 term is coming from?
If the particles have non-trivial angular momenta with respect to some center.
So it's just that. It's just that
Yes,
it's
sir.
coupling both the momentum and the angular momentum.
Yeah.
together.
Yeah. Exactly.
But still just
Yeah.
okay.
But it's not like something is radiating which is also radiating.
No, it's not that at all. Yes. Yes. Okay, so now I want to check these three things, that n is large and so let us try to estimate this. Yeah.
In the gravity case, because we're really solving the equations of motion, there's also this other phenomenon that when two particles scatter, even when they're far away, they can't exactly move in straight lines.
But in d greater than 4.
You're saying it's such a small effect that you can put it.
Yeah, because there is no Coulombic 1 by r effect.
So 1 by r square you can put it.
Yeah.
So there is some deceleration, but that doesn't.
That 1 by r square doesn't matter, and that 1 by r is what makes d equal to 4 more.
Okay, so this d equals 4 is what will give rise to your design.
Yeah,
1 by r.
yes.
So it's such a short circuit.
Yeah. Okay, so now I want to check one by one these three assumptions, and then we have the kind of one of the main results. So let me try to estimate n. So remember we just said n is in. Yeah.
Long range Coulomb interaction is there also for QED.
Yes, it's the same effect. D equal to 4. That effect will be there for QD also.
But the way I was thinking of it in QED, you're allowed to choose probe particles to have any trajectory. You're allowed to specify the trajectory completely by hand, because you can put a motor on it. And the only charge particles. In gravity, you're not allowing yourself. So you have to have this.
Okay, I see. But yeah, but if you just allow them to interact with electromagnet, they even there.
Yes. But you need not do that.
You need not.
just do whatever you want.
Yeah, you can just cancel it out. With
You
some.
just set arbitrary.
Yeah.
That's a slowing down effect only.
Yeah.
I mean, presumably the formula Jackson is for arbitrary.
Yeah, so that the leading soft factor is not sensitive to the IR divergence anyway. Actually, yeah, it's only from the subleading. So in fact, the interesting thing you are asking about Jackson, just one thing is that in the Jackson case, he computed the flux only at leading order in omega, so he got this S0. If he had just, because he had no motivation to go one order above, if he had gone one order above, he would have seen S1 for electromagnetism.
Which is not universal.
Which is not universal, but the fact is that the non-universality of S1 comes from the sort of the microscopic structure of the charges. If the impact parameter is large, only the universal part contributes. So that you can check. If you just, in Jackson, if you go to one order, then so this n is the same as f, which is given by so I would like to estimate this. So let's try to put some parameters for masses, etc. So let's say that the masses, all the masses of the external particles scale is some mu, which is large in Planck units, and let's say that the angular momentum, which is what features in S1, let's say that scales as some mu lambda. So lambda is some impact parameter. Scale of the impact parameter. Then the characteristic frequency will go as lambda inverse. So then we can define the soft frequency as something which is much less than this, which will scale as lambda inverse times tau. Tau is some parameter much less than 1. And so now we have all the, so given a width delta, given a solid angle delta omega, we can estimate what this n is. by just substituting this thing right here. And then n turns out to be equal to, just write it down. These powers I shouldn't mess up because. I can't read my own notes. Yeah. So n scales as lambda to the minus p minus 2. I just substitute all these things here in this formula, and then I just write it down. Tau to the d minus 2 mu square delta. I mean, these are some fixed things, so they don't matter. So whether n is large or not, tau is of course small. So whether n is large or tau is small but fixed. So whether n is large or not depends on lambda and mu. What is the relationship of lambda and mu? And that we can determine. So suppose I say that lambda is because lambda has to be greater than the Schwarzschild radius of the object. So lambda has to be we can write lambda as mu to the 1 by d minus 3 times some sigma. So sigma is some number which is greater than or equal to 1. Does it make sense? Because lambda is just the impact parameter. So the least value is of course the Schwarzschild radius of the particle, and then but it could be much larger. So that information is in this number sigma. So then when I substitute this here, what I see is that n will scale as so I just substitute this there, and then I will get, let me just do that. So I will get mu to the minus b minus 2 b minus 3 mu square tau to the d minus 2 and sigma b minus 2. So this goes as yeah, some sorry, I haven't written it down, some positive power, I think. Is it going as mu to the d minus 2 by d minus 3 tau to the d minus, sorry, I made some mistake. 2 d minus 4, is it? Yeah, and tau to the d minus 2 delta, sorry about this, delta omega, and then actually this I think I made a mistake. Okay, but now we see that so for large mu, if tau is some fixed small number, but for large, as mu becomes large, n scales as a positive power of mu. So that's why with mu, this is the scaling of n with the mass of the particle. Tau is the one that tells you that, so your omega is lambda inverse tau. I mean scales as lambda inverse tau. So lambda is the impact parameter. So this is the frequency, the sort of typical frequency of radiation. So we are looking at soft. So tau is a parameter much less than 1. But tau, we are not varying tau. We just fix a number tau much less than 1, and that tells us what is our soft radiation. So sorry, I messed this up a bit. But yeah, so this is the point that somehow n scales with. So that checks out our first solution. I make a mistake here. This d minus 4. Sorry. Okay, now we want to check what is how are these two conditions satisfied. So let me first make the claim that actually 3, we will first check 3. We see how delta E radiated is much less than mu. Mu is the typical mass scale in the system. And then that would naturally imply 2 is satisfied. I mean this is something we will see. I mean intuitively, as I told you, that kind of expected that if 3 is satisfied, if the total energy radiated is small, then contact terms are small, because contact term comes from soft graviton being emitted from soft graviton.
So
Yeah.
when we were not discussing this in a large N and calculating this one, so when we say order omega, omega square, blah blah, etc.
Yes.
So that was like omega by p.
Yes.
Wasn't it? So like
Well,
omega
well,
by mu. No?
Well, the expansion parameter here is, it depends. It depends on which is, so you have, if A is the Schwarzschild radius of your star, if the impact parameter is, you have 2 scales in the system. One is omega A, which is a number, or omega B. Omega B is the impact parameter and A is the Schwarzschild radius. So the expansion is in whatever is smaller.
So this ensures trivially that omega is much less than mu. Is that right? I mean, going by the previous discussion.
This would be right, because lambda will be u to the 1 by d minus 3. So tau is a number which is much smaller than 1. So this sets the relationship between omega and mu.
So what mu is the mass?
Yeah, typical scale of the masses.
But is dimension versus mass? Or
Yeah, mass, yes.
I'm getting confused. There should be a fractional part. The fractional parts of the masses should cancel.
Yeah, they should cancel. You are right. Yeah. So this is
Sorry, yeah.
well, mu. Sorry. Mu is a mass in Planck unit. So mu is okay. I mean mu is dimensionless. Yeah. Sorry. Yeah. But is that okay for you? So omega is, omega will be much smaller
this
than the.
is your condition that omega is much less than lambda inverse. The
Exactly.
by the
And lambda inverse is essentially mu. I mean mu to the 1 by d minus 3.
And lambda inverse is related to the mass like that, and which also ensures that, I mean, I would have, okay, so mu of course is dimensionless. So I would have thought that omega should be, so there are these hard momenta,
Yeah.
and omega are the soft guys.
Yeah.
So the hard momenta have some scale characteristics.
Yes.
I thought that was mu or not?
Yeah, that is mu. I agree. Yes, that is mu. But lambda,
So,
lambda is dictated by 2 things. One is the mass of the particles, but also the impact parameter. So lambda could be much larger. So if your impact parameter is some b, then the characteristic frequency
so you're saying this trivially
is trivially
condition
is
that,
satisfied.
it's
Yeah.
much less than the hard.
Yeah, exactly. Because if the impact parameter is large, and we are saying that omega is much less than inverse of the impact parameter, and if the impact parameter is much larger than Schwarzschild radius, your
Okay, I
inequality
see.
is trivially satisfied.
Okay.
The classical Einstein equations have an effective scale, right? So if you turn n into the strength of the gravitational field, then this formula should just turn into that scaling scale. You know what I mean? Newton's constant is there, but it's just overall. This
Yeah.
is like the classical equation.
Yeah.
The classical equations, you scale mass, you scale.
Yes.
So this statement, if you just turn n into the classical field, I'm not sure what that conversion was.
So n is the number of as you were saying, e to the n a dagger. That was the coherent shape.
H, the fluctuation is proportional to n.
The fluctuation in
H mu.
oh, okay. Well, h mu nu is proportional to, in some sense, square root of n. I mean, we will see. I will come to this. H mu nu will be really given by. So remember, n went as mod S0 plus S1 square. But we will see that h mu nu will really go as S0 plus S1.
Okay. I was just thinking that when we express everything in terms of H mu nu, this Planck scale should drop out. At least properly normalized.
Yes.
This
Yes.
Planck scale should drop out, and then
Yes.
you just see that this is a state. What you've written there is a statement of the scaling of
The
classical.
I'm sure this is true. We can discuss it. Yeah.
Something like the classical intensity.
Yeah, exactly. And that since there's no scale, no intrinsic scale in the classical equation,
just to emphasize, Gautam, what you asked, so the expansion parameter is either omega A or omega B, whichever is larger. A is the Schwarzschild radius of the masses and B is the impact parameter. Yeah.
Yeah, this fractional powers were thrown me off here because I can see the omega by mu, but now there are this fractional
1 by
powers.
D minus 3 and all.
Yeah, yeah. So if they, it's just given by the mass, then but it's going to be all coming out.
Yeah, I mean, I would say that this is the easiest way to understand it. Yeah, whichever is larger, you take that as a.
So you already said that the impact parameter has to be much larger than the first. So those are the only things for which.
There are two possibilities. One possibility is impact parameter much larger, or we are in the probe limit. Yeah.
Right, one more question. If we're in the possibility that the impact parameter is much larger,
Yes.
then we could just systematically 1 over impact parameter work out the whole radius.
Yes. Exactly. Yes.
And then check this.
Exactly. Yeah.
Moreover, the same parameter, namely 1 over impact parameter, is governing. I mean, at some point in this expansion, this formula will break down at some finite order.
Yeah. In the frequency, you mean in the impact parameter?
No, in just let's say that we take impact parameter divided by Schwarzschild radius of the two vectors. It's capital of two vectors.
Yeah.
We take impact parameter divided by Schwarzschild radius, so that's or Schwarzschild radius divided by impact parameter.
Yeah.
That's a small number.
Yeah.
Now, systematically in this small number, it would be easy to work out the full radius.
Yes. Yes.
Okay?
Yes.
And I was wondering whether your formula, would apply to every order of this expansion, or will stop at the
So this, that is a very good. So the expansion is really in omega B. So we have to rearrange the expansion you are saying in. I mean the expansion causes 1 by omega B plus order omega B plus blah blah blah.
Your expansion.
Yeah. Yeah.
However, the expansion I was suggesting
Yeah,
will just work in my pattern.
Yeah.
That is
B by mass.
divided by
Yeah.
pattern.
Yeah.
So in that parameter, I could systematically do any order work out the radiation, not just soft, but all.
All radiation. Yeah. But you want to compare the two now. Yes.
Yeah, and now I was wondering if I work my expansion out
Yeah.
to some finite order,
Yeah.
is your formula expected to work only at up to some order in my expansion or more than it?
Yeah. I would. My guess would be only up to some order. But
Because
yeah.
it's going away from the,
Yeah.
because otherwise the other radiation.
He will come out. Start coming out. Yeah.
So, even for small order.
Well, he doesn't have omega in there. He's saying that for any omega.
You want to compare only for small.
But I was
But-
thinking even for small omega, because at some point, when the fraction of hard radiation becomes significant,
That's the point. Yeah.
you're ignoring it. So, some order I would imagine that would be.
So small omega comes into some higher order transfer.
Is that right?
Well, I mean
Well,
if the impact parameter is much larger than the Schwarzschild radius, then I think I think then for soft radiation your formula, because there will never be a back reaction in that sense, because we are saying that we will ensure that the total energy radiated is always soft in that.
always small.
Yeah.
I see. So you're saying that okay, good.
That sigma, right? That sigma is parameterizing.
Yeah, sigma is precisely parameterizing the.
Right?
Yeah.
So here you are assuming it to be of order 1, right?
No, greater than or equal to 1. It can be. In fact, we will see that for it to satisfy this condition, it has to be large.
Yeah.
It has to be large. Yeah.
But then sigma inverse is
His parameter is
Sigma inverse.
sigma inverse. Yeah.
then it's not having to be very small.
Sigma is we will see sigma has to be large. So sigma, yeah.
Yeah. But I think it could be of order 1.
No, it could not be. We will see now. This n did not put any constraint on sigma, but when we put this condition, we'll see that sigma has to be large.
I suppose my question is equivalent to the question of, in this impact parameter thing, approximately what is the amplitude of emitting a fraction of the energy in finite angular momentum? That's right, finite energy. Because that's what you're ignoring.
Yeah, I think exactly. So I think you are asking what is delta E, ratio of delta E total by mu. I think that's what, is that what you are asking?
I suppose. What would
Mu is the typical mass of the, right? This is what you are
Yeah,
asking.
yeah.
So delta E total, okay, let me just, maybe instead of asking this question, let me, so delta E by mu, if you estimate, this turns out to be equal to sigma to the minus d minus 3. So for large sigma,
there will be some finite order at which
Hmm.
this expansion, your formula will come.
in this, yeah,
Yes.
in this.
Fine.
Okay, that's what you were saying.
Yeah.
Okay.
V minus 3. And then of course you could systematically correct your formula by taking account the half range
Yeah.
in this example. And once you systematically correct it, you will continue. So in particular,
Yes, your expansion scale is this one,
Yeah.
and B.
and so in particular d equals 5, it will break down quite fast. Yeah.
What happened to tau?
Well, tau, I mean, tau is not something that, I mean, we say that for a given, our statements are for a given bin and for a given tau. So we just choose tau to be some small number, and then we make all the statements. Yeah. So, okay, so let's see, I already told you this now, so I will not, I mean, you have to again take all the parameters, put it in delta E total, and then you can estimate this. So you just take my word for it. This is true. This is not a very complicated calculation. The difference between delta E total and delta E bin is that delta E bin was for, so delta E bin is for a given delta omega and delta and tau. Because so total energy radiated is means you have to take delta omega to be 2 pi, because overall take tau to be 1 and tau to be 1. So that gives you basically gives you an estimate of the total energy radiated, and that you can show its ratio with mu. What Shiraz was asking turned out to be this.
Yeah, I think again this is a statement dimension. That this you will just get that. I mean by scale.
By scaling.
Scaling.
Okay, so and okay, I will skip the next part, but basically now you can show that if you estimate contact terms, you can show that the contact terms again scaling exactly goes like this, no other power, only sigma to the minus d minus 3. So ensuring that total energy radiated is small actually ensures contact term are also small. So once we ensure that mu is large and sigma is large, then all the three conditions are actually satisfied. In a number is large and scales with mu, the contact terms can be neglected, and the total energy radiated in the radiation is small. So that means our soft theorem result is kind of reliable to compute classical radiation. This one? Because I guess what Yashira is saying, what else could it be? Is that what?
Yeah, the difficult thing is that in the end, in the formula for energy, you have to put in the right formula. But you know, if you assume that the energy is some classical field, then 1 over d,
Yeah.
that will give you some power d minus 2 or something like that. So whatever else has to be there has to scale like the power that eats up d Newton and things become there. Then if you assume that thing is proportional to the mass, then what else? You see mass at known factor of d Newton, so this is classical formula, times the only thing left is
Yeah. You are taking ratio with the mass anyway, so mass is not there. So okay, so let me. Yeah.
Differential cross-section.
Yeah.
So normally I would expect that the softest guys will be very close to the mean, that kind of stuff. And in the sense that, like in an accelerator thing, you have this hard PT cutoffs automatically weed out
Yes.
the hard part of the radiation. So
But the soft nature is not.
no such issue here. It solves the symmetry factor and so on. I mean,
But the width of the, I mean, you're saying that the sort of the delta omega somehow is correlated with the softness. That is not. I don't think that is true.
maybe another reason of this.
I'm just picking one delta omega and I'm asking how much soft radiation is coming in. That's all. I mean, of course, if I increase delta omega, of course, it increases.
I mean, if I have two particles colliding, then or maybe colliding like head-on like this, then the hardest the particles which are emitted
Yeah.
are the ones which are nearly at right angles.
Okay.
And the stuff which is all hugging the the beam direction, they are soft.
Yeah. That is correct, because you see that in the soft factor these dot products appear. So I think that's what you are, because if you take S0, that has p nu by p dot k. This k is the momentum of the soft graviton.
Yeah.
And now we are saying that we are fixing this bin around the direction k hat.
Yes, yes, I see. So, oftentimes this is the way to cut out very high energy particle emissions. So,
You are saying that you look at one particular direction.
In this calculation that you were talking about, comparing the hard part of the radiation with the soft part of the radiation, the angular dependence should come in somehow.
But comparing the hard part, I am comparing the total hard part. So I am summing over all the angles.
But suppose you didn't.
Then what we had was this bin thing. There is angular dependence, certainly. No? In the script F, because the script F goes as, sorry, I erased it, I will write it down.
I'm saying that then your classical calculation can be made to go through for many orders, because you are killing the hard radiation anyway, just by choosing the angle near the. Choosing your delta omega to be very small.
But even if I choose my delta omega to be small,
Right.
if the energy emitted in the other directions is significant enough, that itself will emit further soft radiation in this direction. That is it. Okay, so let me just, so this was so for d greater than 4, this is the statement we have, that the classical flux, I'm just summarizing the result now, in a given bin is given by, I will write down the full formula. So again it's 1 over 2 pi omega e minus 1 over 2 omega r e minus 2 delta omega mod S0 plus S1 square. And so nice thing about this is that this if you are really interested in this soft flux, then what this theorem is telling you is that you don't have to know about details of the scattering process at all, because S0 and S1 only depend on asymptotics of the particle. Okay, and then we can check it in a number of cases. Let me just tell you one example, which is a sort of a nice one. Simplest one. I think this is exactly the one that Shiraz had in mind. So the idea is, suppose we take the following case. Suppose we take two masses. So okay, now what I want to do is check whether this, this formula obviously we have kind of derived with a lot of assumption, and then we kind of argue they are self-consistent. So it will be good to check it as many examples as possible.
And
So
purely classical.
purely classically, without doing any quantum. Yeah. So the idea is that we take as many classical examples we can, and then try to compute soft radiation and see if it works, the formula works. So one nice example, the simplest example that we can think about is the following: is that suppose you take two massive particles, and they come, and they let me draw the picture, and then I will explain. So this is so remember that. Sorry, I did not say, I skipped one important point, but yeah, let me. The fact that this, remember what we just discussed was that sigma has to be large for condition 2 and 3 to be satisfied. But what is sigma? Sigma is, so lambda was, lambda was mu to the 1 by d minus 3 sigma, right? So if sigma is large, means impact parameter is large. That is one way sigma could be large, if by making impact parameter to be large. Another way to make sigma large is, if you take your sigma, so suppose you have two particles, and suppose mu is the mass of one particle, let me call it m. And then I take my sigma to be mass of the other particle, m by n to the power 1 by d minus 3. Again a dimensionless parameter. Then you can see that, then again lambda, so then in that case, sorry, let me recap what I'm saying. Suppose your lambda was same as Schwarzschild radius of one of the masses. So suppose you are in a regime where lambda is m to the 1 by d minus 3. Lambda is the impact parameter, and this mu is the mass of the other particle. So let it's 1 over m by m to the power 1 by d minus 3. Then sigma becomes m by m to the power 1 by d minus 3, which will be large if this mass is much greater than this mass. So this is another case in which our formula will be valid. So there are two cases, one large impact parameter and one what we call probe limit. Okay. So now
in both cases you could just systematically work out the full radiation. Right? Because in this case it would be the leading term would be a geodesic in the black hole background.
Yeah.
And then you get
yeah, but the full radiation will start depending on some at some point in the detail, more and more detail of the process. Yeah.
Right.
So the soft theorem tell you to what order we can go when we don't have to worry about what is happening in the bulk in some
But I'm
sense.
saying in both cases you could systematically.
You can do it, yeah. So this case that I'm looking at is large impact parameter. So the masses can be comparable. We don't have probe limit or anything. So you have 4 particles, P1, P2, and then they come, collide, and then you go to P3, P4. Now this picture is very misleading because it looks like how is large impact parameter. It almost looks like they are colliding. But what we mean by this picture is the following: that you have 2 masses with some Schwarzschild radius, say A, and suppose they are very far apart. So we are completely neglecting gravitational interaction between them, and they are neutral. So there is no electromagnetic interaction or anything. So they are basically moving in straight line. And we say that when they hit, they come a distance d, which is much larger than A. Some hard repulsion sets in, and this hard repulsion is basically a sort of short range around B. So it sets in, then they sort of move together, and then they split again. So it's some fictitious model that we are considering. Nowhere gravity is important, neither in this region, neither here, neither here. Is that making sense?
I didn't understand. No,
Oh.
I thought you can have gravitational interaction.
No. These are just they are too fast. So we can ignore gravitational interaction to leading order. They are moving. This is the simplest one. Then we can start looking at the gravitational one later. So here in this picture, the stress tensor is completely localized along the world line.
So it's a limit in which the non-gravitational forces are much larger than the gravitational.
Much larger gravitational.
So that also gives you some system.
Yeah.
But
By the way,
Yeah.
basic question. This merger forces, this approach is not valid anymore with impact parameter or the sigma being large.
Sigma will large can still be valid. It depends on the relative masses of the. But certainly the impact parameter is not valid, of course. Large impact parameter regime is not valid, of course.
Sigma out can sigma be.
I mean, in this extreme mass ratio limit, if you have like one black hole much larger, massive, much more massive than the other. I mean, one thing is that one important caveat. We can't directly apply any of these formulas there anyway because that's a bound state problem, the inspiral problem. I mean, the usual binary black hole merger that you have in mind is a bound state problem. We are looking at scattering processes.
Where was the value?
The soft theorem.
So you cannot have 3 hard.
You can no you can have, but you can't. You really have to start from. It's a scattering process, right? You start far away, come together, collide, and then go far away. If you are just starting at some finite distance and orbiting, then we don't know how to formulate. I mean,
some sort of 2 to 1.
2 to 1 we can do. Yeah, 2 to 1 we can do in the sense that if you have two black holes, one black hole much massive than the other, they are coming from far away, and they just bump and then merge. That certainly apply. We can apply.
2 to 1 will violate kinematics unless you also take the property of the
Yeah.
Typically 2 to 1 cannot be satisfied. Kinematically.
But if the extreme mass ratio, it will be satisfied because then sigma will always be large.
No, I mean just if you want to satisfy both momentum and energy conservation
Yes.
for known masses of 2 to 1, in general it's hard. I mean something else has to be.
So you have two particles coming, colliding. They are moving in as a black hole together,
Right.
and then some radiation is emitted.
But you need to counter that radiation.
That's the soft radiation.
No, but then you need to counter some hard radiation also, because the energy and momentum conservation will be badly violated.
Because the energy of
But-
radiation will now probably be the same order as the energy of the mass. So this
No. Because of the
You're saying that if you think of it as a reverse process, a
yeah
decay process,
decay process.
that clearly satisfies. And in the case where there is not much energy radiated, it's exactly that.
Yeah,
I
we can check it also.
No, no, I
Yeah.
see.
Okay, so in this case, we can write down actually this formula for the flux gravitational flux emitted. So sorry, but what we can do is now, these are, as Shiraj is saying, these are purely classical calculation we can do. So calculation we want to do is the following. We say that.
Just one comment.
Yeah.
Where my main point went from is that from this point of view, the mass of the final die will be tuned
Yeah.
so that the kinematics.
It's yeah.
So it's not like new one decay or something when you know the mass.
Yeah, I thought that even for decay, I mean, the neutrino was needed precisely because of this. 122, it was giving problems with.
No, that's okay. He's saying that, but
How to prove the masses
yeah.
particles, tune them in a way so that it's
So the radiation may be finite energy radiation. Then one. Yeah. Shah's question: is there a possible kinematics in which radiation is only soft? Yeah. So in this case, so what we want to do? So the stress tensor is only localized on the world line because no other fields are present. The particles always stay far away. So then what we want to compute is this. I mean, this usual trace reverse metric.
I mean, this sounds like a weird model to me. Why don't we just take the gravitation?
Yeah, we can. It's a I mean
that's a much more natural thing, right? That happens all the time.
Yeah, I'll discuss. I mean, this one is sort of very easy to.
Somebody had done it before.
Well, so Weinberg looked at the following one, which was that he just looked at this one.
Okay.
So this one, if you do, because this is not present, if you choose this as your center, then angular momentum is not there, initially or finally. Then S1 is absent. So this was a.
That's an extension of that.
Yeah, this is a.
Okay.
I mean, they come together, they kind of move collinearly together, and then they again.
Is this like a phi-q interaction whose coupling is much bigger than deletion? Is there?
Yeah, I would think so. Yeah, but I mean, it's like short ranged. The range is B, but it's like just. I mean, once they move far away, they are again free. Even from that, they are just moving linearly.
It's like a potential well, but how do you get that to be sticky?
Yeah, we haven't.
It's still very weird one. But then, okay,
Yeah, it's a very baby toy model. I mean,
Okay.
so Weinberg had this one.
Sorry, not
So-
phi-q. It's like
Not phi-q.
localized interaction.
Yeah, localized exactly in this B width. Yeah.
Coupling constant itself is a pointy city button. Yeah.
It's keeping me looking at the how does this work?
Well, it's ripples.
They're completely, as far as I'm concerned, they're completely ignoring gravity.
Yeah, completely ignoring gravity.
So it's tug of war.
And then you can how does it go at that?
As long as it's consistent.
Yeah, as long as at every point momentum conservation satisfied, we are happy. So we want to compute. So if I take E alpha beta as H alpha beta minus 1 by D minus 2 trace H eta alpha beta, then this E alpha beta we can compute at any point x. Just classical. This is exactly what Shiraj was saying. D dx prime, some Green's function, retarded Green's function is classical theory. So x prime E alpha beta. But now what we want to do is compute this, and of course we know this in D dimension. We can write down in momentum space easily. Gr x prime is just GL. And then we have the VIL dot x minus x prime by. But this is retarded, so just that.
And because we're completely ignoring gravity,
Yeah.
stress tests are purely the matter stress.
Just exactly. And T alpha beta is just x is just integral d sigma delta 4 x minus r sigma p alpha sigma p beta v beta sigma. Where this sigma is basically what you have to sum out all the trajectories of the particle. So this is so you just take this, you substitute here. So this is an algorithm that you can follow for any example. Now I'm just giving one here, and now just I mean it's m v alpha v beta, one m I absorbed in p and then one v I keep.
And it's clear that thing is conserved. That's obvious, right? I mean, at the point that they.
Well, yeah, I mean. we are assuming that this, yeah, you are right. You are right. At this point, you are saying, right? I mean, because some, but okay, okay. But what we are saying is that the contribution of the whatever is not conserved will be less for the.
Okay. So, but
That's the point. Yeah.
But now when you do this convoluting the Green function, you get an answer that in detail depends on your weight.
Oh, I will come to that point. Yeah, very good. Yeah. So, but then what we can do is we look at traceless transverse piece of the. Yeah. Okay. That's a very good point. So, soft factors are gauge invariant, but E is not gauge invariant. So, some of this relation I have to explain a bit.
Well, I think there's a series, I mean, in principle, applying this formula to something that's not conserved, in principle, is a bad thing. And you're saying the bad part.
Bad part is smaller.
Is small, so you forget about it.
Yeah.
It's a bad thing to do because you work in different gauges, you get in detail different answers for physical things.
That's not solvable, but we can still have this process, right?
No, the process is okay, but they are saying that.
What is the stress
Obviously
tensor
the-
corresponding to the process?
Yeah.
When you solve Einstein equations,
Yeah.
unless you have a conserved
Yeah.
stress tensor on the right hand side, you get an inconsistent.
So there is this other field which we are kind of ignoring, which is the short range field at a distance b. But what we are saying is that doesn't, because we are going to measure gravitational field large distances, that contribution to the stress tensor will not matter to the soft radiation. That's all.
This is why I think it's a weird model. I mean, why don't you just do none?
Yeah, now I'm regretting actually doing this one. No. The reason this model is slightly interesting is that we can generalize it a little more in the sense that now we put charge on this. Then there is electromagnetic interaction between them. Then the stress tensor has this and the stress tensor of the electromagnetic field.
But just it would be harder, maybe more work to do the calculation, but maybe that's the point. But if you look at Reisner non-stop black holes coming in,
Yeah.
they would have charge, they would have. So that would be a totally genuine calculation.
Yeah. So
Yeah.
I will discuss. Yeah. So
This steady field is like the particles are carrying some jet packs.
yeah.
So that there is an external force, I don't know anything about them, and because they're carrying some jet packs, I can ensure such trajectory that is infinity.
Okay.
And the problem is that you're ignoring the stress tensor prediction.
Jet. Yeah.
That's the problem.
Yeah.
That's the thing. And you were saying that the stress tensor of the jet pack.
It doesn't matter.
It
For-
doesn't matter.
for-
I mean, it's smaller than.
Smaller. Yeah. But yeah, there's something to yeah. So bad model. So now the procedure here is that please I mean okay, let's let's accept the limitation, but the procedure is very general. So given any t, what we are interested in is the following thing. We are interested in looking at the radiative part. So I will call it E alpha beta radiative. I will explain what I mean. In frequency space at some point x. But whereby radiative I mean the power. So if I take mod x to be r, I am interested in that power which falls off slowest. So in d dimension, the slowest fall off will be given by 1 over r to the d minus 3. So that's what I am interested in. I am interested in the radiative field, the field which dies off slowest as I go to large distances and at a frequency omega. That's what. So then what you can do is if you take x to be large, mod x to be large, then you can apply saddle point. I'm just giving you some words. So you can do this integration nicely, and in the end you get the following result. So E alpha beta radiative omega x is given by some normalization factor. I will just write it again. It will be omega r. And then I will write the result. E alpha. The indices are raised and lower, we have to do eta. So don't worry so much about the plus. Sorry, 1 second. So okay, PA alpha sorry, I will explain what I am doing. So this term, as you can see, is clearly the related to the leading soft factor, and you're summing over all the incoming and outgoing particles. If you look at this term, I'm only summing over 3 and 4. So if I choose my, the reason that happens is that if I choose my origin of my coordinate system here and I call this point E, then you can see that this PA alpha is common in both these terms, and what I'm getting here is R beta P gamma minus R gamma P beta. So that's an orbital angular momentum of these two outgoing particles. So this factor is really the subleading soft graviton factor, which means that if I now contract this with my polarization, so if I look at epsilon alpha beta, E alpha beta, then what I get is n, some normalization. This normalization involves this 1 over r to the d minus 3, all those factors I am not writing down, e to the I omega r S0 plus S1. So that's what where S0 is the leading. Yes.
So I think I just missed a little bit. So just to, you're taking a Fourier transform of this?
Yeah, so this is of course Tx.
Yeah, then you
Just Fourier transform T,
T
and then large X. Large X.
and then low energy, which will then do some saddle point approximation of that.
Yeah, you take exactly. You do Fourier transform. You look at once you do that, and then you do saddle for large X, and then you look at terms up to order omega to the 0. So you get this result. So this result tells you that the radiative field really looks like this. And now if you compute from here the flux, you can show that with the normalization you precisely get the flux that we had.
Could I ask, since you're not worrying about energy stress tensor conservation,
Yeah.
you could have chosen arbitrary paths for your two particles.
Yeah, no, it should work for any, exactly the process. This was just one where this integration, I mean, you could do it explicitly nicely.
If you choose arbitrary paths,
Yeah.
ignoring the issue about the stress tensor conservation, it should then turn into the Jackson problem. Effectively. Because that's presumably what Jackson did for electromagnetic.
What you are saying is that okay, let me try to say something. Maybe that's what you are talking about. So for electromagnetism, you will write down the radiative field for arbitrary trajectory for a probe particle. So you have for a probe particle.
That's essentially what you're doing here. Right? You're treating this as a probe particle.
No, these are both of equal masses. I mean, yeah, okay.
But you're not taking into account back reaction.
You are not taking into account.
So it's essentially probe particle.
Okay.
What you've done effectively is choose
Yeah.
particular trajectory. But
Yeah.
if you've chosen, but I thought the problem with choosing trajectories is because the stress tensor is not enough.
Yeah.
But since you're ignoring that, you can choose arbitrary trajectories, and then that will turn into more or less Jackson's problem. With slightly different source, like extra factors are extra. So you could then ask the more general question about whether for arbitrary trajectories, ignoring this issue, the formula works.
Yeah. Yeah, so let's look at this example. So if you take, for example, a black hole of mass m, and you have a probe particle, some very small mass m, and moving at a large impact parameter, b, then you can write down an integral expression for.
I can all approximation, right?
Yeah, and that's a very messy thing because all the stress tensor of gravity, everything contributes to the radiation.
Yes. So
Now you can check
the example, and then you can just check.
Yeah. This is an example where the integral is very complicated, but from that integral you can actually check explicitly that this formula is reproduced. But
that sounds great, and this is probably a problem that people have worked out.
yeah, this was done so this is I was about to come to this. So in 4 dimension, this was done in a really remarkable paper by P.C. Peters. So this is kind of the sort of the starting paper for the numerical relativity guys. So he gave an analytic expression for radiative field at finite frequency, not soft or anything, but they were all integrals. I mean, he couldn't obviously solve them, but it's all there. So if you take that, but it was in 4 dimension. So if you take that and you go to the leading order, so you compute, he gives you an integral formula for this, which is like a dozen terms. But if you go to leading order in omega, then you get precisely S0, nothing else. Now if you go to subleading order, you can see that this expansion breaks down and you get something which is proportional to log omega as opposed to S1.
And this is the acceleration, deceleration.
This is because of the Coulombic effect. So that tells you that so classically that formula is finite and well defined, but that tells you that the soft theorem sort of has a log thing that.
But this Peter's problem has not been solved by somebody in arbitrary dimension.
We couldn't find, yeah. But we look at some other examples of some high energy scattering in presence of branes or something where these formulas were.
Just as a gravitational question, somebody should solve that problem.
Yeah, we searched a lot, we couldn't find.
Sounds like an MSc thesis. I don't know why they would.
Yeah. Some of them are interested actually. Yeah, but some of Peter's this setup no one has really know.
It's a very natural question.
Very natural question.
Theory of gravity.
Yeah,
So this problem is the same as the previous one, except that the particles now move around.
but it's a Schwarzschild background. You're a Schwarzschild background, so the Green's function is very complicated.
Along the genuine geodesic,
Yeah,
and you will take into account the stress tensor,
Stress tensor of
also,
the
curve.
curved background.
So this
Yeah,
is totally genuine stuff. Well posed.
yes, yeah. And his formula. In fact, there is a So let me. How much?
You're saying because of the way you're taking the limits,
Yeah,
what only should matter is the asymptotic structure of these.
for the in the soft limit.
For these geodesics.
Yes, exactly. But some of the formula we don't know. I mean, if you look at his formula, this is finite frequency, so it's very complicated. But then you check that actually indeed this is true.
So in a general problem, I don't necessarily need to know the full geodesic or anything. As long as the structure is far away.
But-
is
but-
known,
but-
then I can.
But you will have to actually check it. I mean, you have to give me the Green's function, integrate and take the soft limit. That's a hard. I mean, just the Peter's formula is very messy.
Here T is not taken to be supported only.
No. You have the full T. Yeah.
In the largely context, shouldn't there be an enormous significance?
Yeah. That is it. It's too much. Or just three. Let me keep the first. Yeah. But if you keep the first, contract of that. Oh, you make them scatter part of it, the effect is very small. Well, I think the feeling better. But
Okay, so this is the so we can in d greater than 4 we can look at number of other examples. One of the example is which is also, I think now I should not say this, but the another one that is more tractable analytically is you do this, but you let these particles also electromagnetically interact. So there is one more component to the stress tensor which is the stressing of the electromagnetic field. Then it's a more non-trivial calculation because then you have to have a cancellation. So your T has two components, that this of the world line plus T mean of the stress of the electromagnetic field. Then you again compute E alpha beta, and then you see there are some nice cancellations because these particles are no longer free now, they are accelerating under electromagnetic field. So this contribution changes from the world line T mu nu, but that gets cancelled precisely by contribution from here, so that final answer is actually just this answer.
So the world length is how does it change?
No, because the particles are now accelerating under electromagnetic interaction.
They don't have jetpacks.
they have jetpacks also.
Only over that, yeah.
Why can't they have jetpacks? And then because jetpacks don't matter, you're saying.
Yeah, they anyway, yeah, exactly. So now there is what more matters is the electromagnetic interaction.
No, but why can't I just put them on my trajectory and see the probable effect? Giving the same answer.
Okay, yeah, you can do that, yeah. But this is a you see that here the point is we are letting them free and letting them sort of electromagnetic, so the charges are large, so we are letting them electromagnetically interact, still ignoring gravitational interaction.
But and now you take the stress tensor of the whole electromagnetic field.
Field.
So he's doing a little more. He's ignoring the jetpack part there,
Yeah.
but not ignoring the jetpacks here.
Yeah.
No, but you could put them just not accelerating trajectory.
That's what he did first.
First.
Yeah, so you can do the same thing now.
No, but now we would like to do a bit more. I mean, to check the formula. So we are saying that let's take a little more complicated case. Maybe I'm misunderstanding you. Where
No,
the,
I'm just saying that you could just put the particles on your trajectory, not let them free.
Okay.
Not let them be free, and then do the
That can be done, yeah.
And
you
that
can
should
try.
give you the same answer.
That should give you
first,
the low,
first
low.
part will give you that answer.
Yeah.
How will the electromagnetic part not change that answer?
That's
Oh, that is your.
right. Yeah. But you know, now you have
Yeah.
this the stress test is not
Yeah.
being considered.
Yeah.
Some point will really.
Yeah.
Right,
Yeah.
So how we wanted to control the thing.
Somehow here that is not conserved only over race.
Yeah. No, that's the point. Yeah, somehow we have not been able to quantify it, but I think that's what is mattering. Yeah. So if you have stress tensor contribution from everywhere, then you should take into account. But no, but this is a very this is not a very clear statement. Okay, so this is basically completes the analysis for d greater than 4, and this is the final result that the radiative field at low frequency you can write in terms of the soft factor. Now how much time I have?
If we want lunch,
But no, you tell me when to. I mean, this is a good place to stop, but I can. 5. Okay, 5 minutes. I will just say what happens in 4D. So you can see. So you see the S1, as we can see from here, is so. Let me just rewrite S1 again. So it's given by sum over all the external particles. So in this case, for example, 3, 4, and let me just take all. So 1, 2, 4, epsilon. Where this JA nu lambda is given by XA nu JA lambda classically minus, which is what features here, only the classical angular momentum as we saw above, XA lambda nu. And asymptotic, we are only looking at the asymptotic angular momentum. So in higher dimensions, XA nu goes as, let me look at XAI for example. XAI will go as some constant, X vector will go as some constant plus lower order terms. But so that means what contributes to J is only, because this V and P are collinear, so what contributes to J is only this constant vector A, the constant shift A. So that's why J asymptotically J is finite in higher dimensions. But now if you look at in 4 dimension, there is as Shiaz was mentioning, there is a extra Coulombic effect, and your asymptotic trajectory doesn't never becomes linear, but it has an extra effect, a logarithmic effect, which can be written as plus, we just call it some C log mod T, as T goes to this something. Let me put plus minus everywhere. So you can see that now when I substitute this quantity in the angular momentum, in addition to this contribution, which is finite, I get actually a divergent contribution, and that is given by, and that is of course much larger than the finite contribution, and that is given by, so that contribution looks like C plus minus I P plus minus J minus, if I look at contribution coming in J I J, then that contribution looks like this minus log mod P. So this obviously looks like a divergent contribution. So classically you would be a little bit surprised that if this indeed was the result radiative field you were getting, and if you work in omega space, what would this be replaced by, right? If you wanted to do that, I mean and the naive guess you would make is that in the frequency space, this T would be replaced by omega inverse. So the naive guess would be that because this is large time and frequency is small, so it would be replaced by omega inverse. It would be like the 0th order guess you will make. And now you can check that actually this is indeed true for the Peters example. You take Peters example and you look for the next order term, keeping in mind you should try to get something like, I mean, you know that you're seeking answer because they have a lot of integrals, so you have to sort of, it helps to have an answer in your head. And then you can indeed show that your S1 gets replaced, the form of the S1 remains the same. It is the j mu nu etc. But j is now goes as log omega, and once it goes as log omega, the order 1 term is ambiguous now, because log omega is same as log 2 omega, 3 omega, whatever. So the order 1 term that we had before sort of becomes no longer remains universal, it becomes ambiguous. But you can check that this term, in all the classical cases we looked at, this term was indeed universal, the log term. It had a particular form. And now today Ashok and his student had a paper where they show that you can derive this result from the quantum calculation, and it is indeed a universal soft factor. So in 4 dimension, the omega expansion breaks down because of this log omega singularity, and but that factorization is universal.
These should be very easy. I mean, just classical, right? Because it's, as you say, it's the correction. The fact that these things are not quite
Yeah.
fun.
Yeah.
You just Fourier transform that last part, like you're saying.
Yeah.
You should just make the get, and that should be totally. I mean, the fact that that's universal should be.
So,
seems quite clear.
okay. So maybe I should say more. Yeah. You are right. So classical result, you are totally correct because of your argument is universal. But now in higher dimension, we saw that we started from the quantum amplitude, we extremized n, and we saw that we got this candidate classical result, and we checked that it was indeed true in classical theory.
Yes.
Now in 4 dimension, up till today, we didn't have a quantum result at all. So now we are saying that we look at the classical result, and we derive S1, classical S1, and that is our soft factor. And what Ashok and Biswajit show is that from the quantum, what you get is this S1 plus some quantum corrections, but they are quantum corrections, they die down in the classical limit. So the quantum S1 is a log omega term, which is this S1, the one that I just wrote down, plus some extra piece. Both are universal, but the other one are quantum corrections. Yeah, because of the infinite divergences.
So now in the quantum theory, you have the 1 over omega.
And 1 over omega,
You have a log omega term.
yeah.
And then you also have an order 1 term.
But order 1 is now ambiguous.
So now order 1 is ambiguous.
Yeah.
And how do we see that now from asymptotic symmetry? So that if that log term is now universal.
Yeah, so now we have to, that's an important question. Now we have to understand how asymptotic symmetries, we can talk more. I mean, I have a feeling that I can tell you more about this, but I feel super rotations account for this once we take loop corrections to S matrix into it.
So if I do the same, the idea is that the same analysis, but now including loop corrections,
Yeah.
will somehow give rise to
Yeah.
log term
Yeah.
in the soft theory,
Yeah.
but not the order 1 term.
Yeah. So in this way, classical theory became useful also for the quantum soft theorem in 4 dimensions.
This is the classical result.
This is just a classical thing, yeah.
Classical theory also will log.
Log omega, yes, because what I'm saying is that, you see, in D greater than 4 dimension, this is the result for the radiative field. Now, where S1 is, this depends on the orbital angular momentum. Orbital angular momentum has a log t term. So naively you would guess that that log t will become log omega inverse. Now you take a number of classical examples in 4 dimension and you compute, and you get exactly that result in the classical radiative field.
And then what the quantum do, we just
So now you know that in D greater than 4, this is related to the quantum soft theorem. In 4 dimension, we didn't know what was the quantum soft theorem in 4 dimension once we took loop correction into account. So what this told you is that at least one contribution to it was this classical S1 with a log omega, and Ashok and Biswajit showed that is indeed this S1 plus some quantum correction.
And can you explain intuitively why there's any quantum correction? I would have thought this is all such long distance.
Oh, right, okay,
that it
yeah.
should just be that.
So, yeah. So really there are you're saying why there is a, yeah.
And all of it is coming from these guys very far away. Very far away, classically done is very good approach.
So there is another effect, but that is also present in classical theory, which is the so there so you have scattering of particles, and then there is radiation coming out, and then there is a Coulomb drag on this particle by other particle,
Yeah.
which gives rise to this law.
Yeah.
There can also be Coulomb drag on the radiation, which gives rise to a phasing term, but that's also in a classical theory. In addition to both these terms, there is a extra quantum contribution that that is there in the today Ashok's paper. Maybe we can take a look. I mean, yeah, I can't quite recall, but they have an explicit discussion of the physical origin of that quantum, so we can check it. Yeah. Yeah. But you see that the problem was that, that's very yeah, I was also confused about this. But the point is that you see so what Prahar is asking is the following, that before today's work, there was a number of investigations into subleading Soft Graviton theorem once you take loop corrections into account. And people had looked at sort of dimensionally regularized the IR divergence and wrote a result which basically was in fact divergent. So they were getting a soft factor which was IR divergent. And they had no control over the finite terms in the subleading soft factor. So what Strominger has shown is that this IR divergent soft factor has a symmetry origin. But this is kind of it was a scheme dependent quantity. But now what Ashok and Vishwaji have done is that they have really looked at the IR finite cross sections and computed the soft factor. So there is no. No, they do what is known as this Grammar-Yani technique, which is an old technique in QED to really separate out the finite piece from the divergent piece.
So they consider the IR finite S matrix.
When the S matrix is IR divergent, there is a clean separation of the divergent. They still look at the usual S matrix, so there is IR divergent, but all the IR divergence is factorized as exponential factor, and there is a IR finite term, and from that IR finite term you extract out the soft.
In that IR finite term, there should not be any S naught, right?
No. If you take S naught will be there, because we are saying that if you take a S matrix, which is IR finite, but we take one particle to be soft. That's why the soft factors come.
But isn't S naught usually?
S naught is universal.
It is universal, but usually you think of S naught as being as being the guy that helps you cancel IR divergences from these, right? I thought S naught is the thing that when you take into account of, so you get IR divergences from the loop,
yes,
and then you take into account of you sum over all the radiative.
The real infrared divergence, you are right.
So all of those things, and the contribution, the leading contribution from S naught, all of those things add up and cancel the loop divergence.
Yes.
Give some sort of IR finite cross section.
Yes, that's in the cross section. But now we are saying that if I take just a scattering amplitude, which has say some 4 particle scattering amplitude, so it has only virtual infrared divergences now because my asymptotic states are fixed. And then if I take one particle to be soft, I get a S naught factor. Just multiply.
So that you the factorization that you have the IR divergent factor, those are all contributions from whatever virtual particles.
Virtual particles, yeah, exactly. Yeah, exactly. So sorry, one thing I remember what Ashok says is that the sort of the back reaction, okay, we can look at the paper. The back reaction effect on the soft particles is what gives rise to this extra quantum correction.
That's not very nice.
Wait.
Wait, one.
Yeah.
Wait. I have one question that Prahad sort of or formulated something. You were looking at the application of this soft theorem to a particular case where you knew the hard stuff is not very important. But there is, as you said, there's a clean statement, which is a formal statement that applies to the classical unit. So it would be nice to have a derivation of that formal statement purely within classical physics.
Okay. That is not available right now.
But it should be true. I was wondering. So the first thing you can ask about the quantum. We know how to classically formulate S matrix. Right? There's positive energy data and square minus, negative energy data and square plus, and you find the action in the function.
Okay.
So this is a purely classical. And now on that classical object, could you apply your covariantization argument? I was just wondering whether you could just run through the derivations that you guys, beautiful derivations that you guys have, in a purely classical context. Never invoking anything quantum, but purely solution lifestyle equation. It sounds like it should work, right?
Yeah, I agree. I mean, certainly if you just have point particle scattering.
I was thinking this first case to start with is just pure Einstein. So the things that are scattering are Graviton.
Okay.
It's a very clean system. Okay. Now there is some statement about the S matrix there. the S matrix, the hard S matrix, is
Yeah.
dressed by these additional factors into soft S.
Okay, yes.
Okay, so this is a very clean system. The equation of motion is R mu nu equal to 0. Some statement about solutions of R mu nu equal to 0.
Yeah, okay.
This is classical differential
Yeah,
equation
yeah.
problem. Should be, since you guys have such great understanding of the complicated quantum problem, should be a piece of cake to. Shouldn't it? I mean,
Yeah, in principle I agree, yes. You are saying that just applying covariantization procedure to the Einstein-Hilbert
yeah,
action.
and it is a very clear context because then you don't have to talk about some effective action. So just
Yeah.
you know exactly what you're doing. You're solving some classical differential equation, and you can prove a theorem in a way that a mathematician will. So I mean, it would be very.
No, you are right, completely. You are saying that so just from there you should be able to get this result.
You should be able to get the abstract result.
Yeah.
That the soft factors dress the hard factors in a particular way.
Okay.
Okay, and then the question of whether you have the control over the hard factors is another thing.
Okay.
So just the abstract result as a purely classical
Yeah.
case, it should be. If you should be able to cleanly prove it, I think.
Yeah, I don't see where it will be different from the effective action because it's just a.
Sorry.
Yeah, yes.
That would be even without worrying about this large number of electrons.
Yeah, he's directly classical. He's talking directly classical.
You know, these straightforward, yeah. Some statement about the classical solution. It would be very small modifications, maybe therefore not even worth it. So maybe it would be nice. So then you don't have to go through all this N and this, all of that, right?
Just do it directly classically. Okay.
Like some statement about the classical differential equation.
Yeah.
So that this is something that defer Morse would have been. Okay, correct.
But would it be applied to a wider range of settings or?
Yeah, he's saying
That
general.
would be
Yeah, completely general.
I think it should be something very straightforward.
Yeah.
Exactly, but they have this trick even for R mu nu equals 0. They found it useful to think of the soft part as covariant and the hard part.
Yeah.
So all of those things that sound like interesting tricks. I mean, somehow you might learn something.
Yeah. Okay.
You might learn something because it's very clear context. There's no assumption.
So assuming solve for the soft part after covariantization, just write the soft part as some abstract
No,
universal.
everything that you guys said, I know you guys said it very clearly and beautifully, but perhaps there was some hidden assumptions in there. Okay? Here it's very clear. You're solving the equation R mu nu equals 0. So you should be able to proceed with, totally step by step. Every statement should just follow from classical differential.
Okay.
There's sometimes value to that because you might realize some subtlety.
Okay. No, I completely agree. I think it should be possible, yeah.
Can multiple soft graviton theorem be derived from the single soft graviton by taking larger numbers of features?
Yeah, but that is as we were asking, that will give you this consecutive limit. So you take one soft, then next soft. So that will be a sub. And the result I gave was general. That will be a subclass of some terms of that will be not be there present.
Use the contact.
In contact, some terms won't be present.
In Alok's presentation, and when covariantization, you can derive any soft whatever order.
Yeah.
No, I'm just saying if you have the result for one.
Yeah. One soft theorem, then you take next soft.
And
So you can.
will get the result.
Well, but then you will
No,
get this.
but if I just give you one soft, how can I use that to derive
No.
simultaneous soft? Double.
That you cannot.
That I cannot.
He's saying consecutive. He's asking about the consecutive. That.
Oh, consecutive.
Yeah. So you just get S0 plus S1, S0 plus S1 like that.
You have to be just slightly, it's exactly that, we should be slightly careful because suppose I take one of them soft, now so I get S0, S1, but S0 contains factors of the second graviton limit.
Yeah.
So it's proportional to the limit. So when I take a double soft limit, I'll get soft factors originating from the amplitude on 4 that we have.
And the
But
soft
also from
previous.
the soft factors because they also have a low energy expansion in the second graviton. So yeah, it can.
But if we take care of this, then I can also derive multiple factors simultaneous.
No, simultaneous you cannot like this because
Simultaneous, not with that.
yeah, they are really independent.
But this covariantization procedure can